So this is one of the classic questions for centrifugal and centripetal forces. You've got some kind of little plumb bob and you're spinning it. It's fixed to a point on the ceiling, something like that. So I've drawn a sketch of that. The sphere has a mass of 5 kilograms. So we know this is 5 kgs. Oops, 5 kilograms. And it's a 3 meter long cable. And it wants us to find the speed to get an angle here of 45 degrees. I'm actually drawing it as 45 degrees, but that's what it's looking for. And it wants us to determine the tension in the cable. That's all good. So what we'd want to do is we probably want to draw a bit of a free body diagram. Just think about what forces we've got acting on this. So we have got centrifugal force. It's going to be, so I'm drawing, yeah, so for this position, do you know what I mean? So it's over here somewhere. For this position, we're going to have a centrifugal force and it's acting radially to the circle this thing is rotating in. So centrifugal force, and we've got a force due to gravity as well. And we know that those two things are equal because it's at 45 degrees. So the reaction is going to be at 45 degrees. The only way we can get a reaction is if that force, those two things are equal. But anyway, we'll get to that in a minute maybe. So we get a reaction that would be in line with the cable. Remember all that stuff. So for a cable, the force is always, the force that can be applied by a cable is always aligned with the cable. But what I'm going to do, that's okay, let's just do it as that. And so we're going to get a reaction force like so. Let's just call that R, or could be tension. Let's call it T. T. Now that is made up of two components. So we're going to have one component in this direction. So we'll call that Tx. I'm doing it dotted, not to show that it's not the right point of application, but just because it's a component of that T. I don't want someone to think that there's like, that was why I was thinking originally. I might just do that. Rather than draw this tension, let's just draw the components of tension. So we've got two components of that tension. So you've got a tension acting like so, and it's going to have X and Y components like so. And because this is 45 degrees, it's going to be quite an easy one to solve. But you could do the same thing. It's just going back to, you know, all the stuff we learned when we're doing particle equilibrium. So even if these two things weren't equal, let's just do it out nicely. So it might be, you know, this thing is not at 90 degrees. It might be more like so. And we'd end up with a reaction like something like this, not at 45 degrees. But you're just using all the theory we've used to figure out, first of all, maybe you'd figure out the resultant of these two forces, and then you'd figure out your reaction is equal and opposite, or you might just think of it as equilibrium to start with. And so you'd resolve this into its components. Then you might have to use simultaneous equations or whatever to try and figure out what those two components were, and you're writing them in terms of T. So even if it's a little bit more complicated in this example, if you go back and look at particle equilibrium, you'll find the method you need to use to solve it. But in this case, it's going to be super easy because this is just equal to that. Even if it wasn't, even if this was bigger, you'd still be able to say Ty is equal to that, Tx is equal to that, which would let you figure out your resultant force using simple trigonometry. So it's going to be easy no matter what those values are. Anyway, we know this is mg, that's the weight of that little sphere. Let's just think, we'll keep going, see what happens here. So we know, let's write some of the stuff down. We know that the centrifugal force is going to be equal to mass times velocity squared over rho. Let's see what else we can figure out. We also know that rho, this value of rho, is going to be equal to 3 times, so opposite over hypotenuse, so it's 3 sine 45. So let's just do that at the side. why I'm doing this in blue. So basically I'm just figuring some stuff out here. So rho is equal to 3 sine 45 degrees, which is equal to 3 sine 45, 2.121, 2.121. We've also been told the mass, I think, haven't we? 5 kilograms. So m is equal to 5 kilograms. We don't know rho. Oh, we've just figured out rho, so that's okay. Yep. So the centrifugal force, FCF, is just going to be equal to 5 times speed squared divided by 2.121, which is the radius of the motion. So 5 divided by 2.121 is 2.357. Now, what else can we do here? Well, we know we can figure out mg as well, I guess. mg is equal to 5 times 9.81, which is equal to 5 times 9.81 is equal to 49.05. And because this theta is 45, the resultant of these two things must be at 45 degrees. Therefore, this is going to be an isosceles triangle. Therefore, these two things must be equal. So Tx is equal to Ty. And therefore, we also know that Tx is equal to FCF and Ty is equal to mg. So we can say that the centripetal force must be equal to the force due to gravity. So for reaction at 45 degrees, FCF must be equal to mg. That means that 2.357 times the velocity squared, or the speed squared, sorry, must be equal to 49.05. Therefore, the velocity must be equal to 49.05 divided by 2.357, which is equal to 20.81, and then we'll take the square root of that. It's 4.56 meter, 4.562 meters per second square meters per second. So velocity, so it's a speed, sorry, speed. I think I've been saying velocity is speed. So therefore, that is the magnitude of the velocity at that instant. Anyway, whatever. So therefore, we've got that. Now, what do we need to do? It wants to know what the tension in the cable would be. So we know that Ty is going to be mg equal to mg, which is equal to this. We're just saying the 49.05, yep. And we also know that the centrifugal force is also 49.05. So therefore, we can figure out, let's just write it down. So the x component is equal to FCF, which is equal to the y component, which is equal to mg, which is equal to 49.05 watt newtons. Therefore, tension in the cable is equal to square root of Tx squared plus Ty squared, which is equal to square root 2 times 49.05, which is equal to root 2 times 49.05 is going to be equal to 9.90. Oops. 9.905 newtons. Interesting. Because I'm an idiot. So it's square root 2 times 49.05 squared. is equal to 63.4 newtons. So 63.4 newtons. So write down our answer. For theta is equal to 45 degrees, the speed equals 4.56 meters per second, and tension in cable equals 63.4 newtons. Makes sense. And I just go back through that, just go through the calcs again as a check this time. There isn't really another way to figure that out or to show that it's true, but we are saying this is 45 degrees, therefore I know my centrifugal force must be equal to my mass. Just quickly, the mass is equal to 5 times 9.81, which is 49.05, and then so therefore we find the resultant of these two things, then we just square root of this squared plus this squared, so it's going to be equal to 49.05 squared times 2, and then we take the square root of that, 69.4. So yeah, yes. Oh, sorry about that. That's why it's worth doing a check. 69.4. 69.4. Just check it that right. Square root 2 times 49.05 squared. 69.4. Cool. Done. So now you can fire on and have a go at the tutorial. There'll be some questions like this in it. Might be a little bit more complicated, but remember, all you need to do is draw your free body diagram and figure out your centrifugal force and your mass, and then use the normal particle equilibrium, even though it's not static equilibrium. But by adding this inertial force, which is only due to the fact that this is accelerating, we kind of turn it back into a static equilibrium problem, or we turn it into an equilibrium problem. It's not a static equilibrium problem, it's an equilibrium problem, because we're converting the acceleration of this into an equivalent force, which is the centrifugal force. Okie dokie.